Okay, let's, in a relatively short Pencast first, kind of look at a broad picture of what we did with differential calculus this semester. We started out talking about an average rate of change of position with respect to time. In the time interval AB. Remember, the context was that we were given S of t, which is a position function for motion along a line, and we computed S of B minus S of A over B minus A. Remember our car example? We made tables of values and we computed average rates of change of position with respect to time in these time intervals. We call this average speed, okay? But if you can change direction, it's really average velocity. This is called average velocity. Our original examples, we did not change direction, so we could call it average speed. But then we generalized it. Now, it was later on in the semester, but we eventually generalized this to any function. The average rate of change of y with respect to x as x changes from x equal a to x equal b is f of b minus f of a over b minus a. But then, think back at the beginning. Didn't we look at these average velocities in time intervals that shrunk down upon a certain instant in time? So what we were really doing was that we were taking the limit as t approached a of s of t minus s of a over t minus a. And that is instantaneous velocity at the instant in time t equal a. We also, later on, took the limit as x approaches a of f of x minus f of a over x minus a. Right here, I'm just replacing the b with x, just like right here, I replace the b with t. And this is our instantaneous rate of change of a function, f of x, with respect to x, at the time x equal a. We called this a derivative. Okay? Now, there was another form of the definition of derivative. This was one of our definitions of derivative. What do? We let h be x minus a and did a transformation of variables. And we got the limit as h approaches 0 of f of x plus h, or a plus h rather, minus f of a over h. And that's just another form of the definition of derivative. We went back and called this f prime of a, and call this f prime of a. Okay? Now, why did we study derivatives? Derivatives have important applications in other fields. Instantaneous rate of change of the output of a function with respect to the input. There are lots of applications in other fields. You got a little bit of a taste of that when you did one of the sections in Chapter 3 on the applications in various other fields. Derivatives are helpful in graphing, right? We can graph a function without using a calculator. Okay? Now, what was the algebraic, what was the geometric application of this? Remember, average rate of change of a function is what? It's just the slope of a secant line connecting 2 points. Instantaneous rate of change of a function at a particular point would just be what? The slope of the line tangent to the graph at that point. That was the geometric application. Okay, this is integral differential calculus in a nutshell, hoping to give you a little perspective on what we did. One important application that, because of the shortened time period of the semester because of the coronavirus and our loss of a week, we did not look at section 4.7, which is optimization. That's another application of derivatives. It's practical and applied, and you find maximum and minimum values of functions. Basically, the idea is you come up with a graph, and then you analyze the graph for high points and low points. If you're interested, or if you're taking Calculus 2, I would suggest that you go back and look at section 4.7.